Hello everybody and welcome to this video where we're going to look at how we can solve an elastic collision exercise given only the information about what happened before the collision. And that is by using the conservation of momentum, which is P equals P prime. So the momentum before is equal to the momentum after the collision. And by using the kinetic energy formula, or the conservation of energy, which is kinetic energy is equal to kinetic energy prime, which means the kinetic energy before the collision is equal to the kinetic energy after the collision. So let's start with the momentum conservation formulas. So P is equal to P prime, the momentum before is equal to the momentum after the collision. So a moving 0.5 kilogram rubber ball elastically collides with another 0.3 kilogram rubber ball. So first we're going to write the given. So we're going to start with MA is equal to 0.5 kilograms and MB is equal to 0.3 kilograms. The first was moving to the right with a speed of 0.4 meters per second. So this means that VA is equal to 0.4 meters per second, like this, while the second was moving at a speed of 0.9 meters per second to the left. So first we're going to make sure that we're indicating the directions properly. So object A was moving to the right, while object B was moving to the left. And that means VB is equal not to 0.9 meters per second, but rather negative 0.9 meters per second. And I remind you why. That's because when you're going in the opposite direction, if you take the positive direction as towards the right, then anything going to the left has to end up being negative. So we say that VB is negative 0.9 meters per second. So now that we have that in check, we're going to start writing down our the expanded form of the formula. So we're going to say MAVA plus MBVB is equal to MAVA prime plus MBVB prime. Next, we're going to plug in our numbers. So we're going to say MA is equal to 0.5 times VA, which is 0.4, plus MB, which is 0.3, times VB, which is negative 0.9. All of this is equal to MA, which is 0.5, times VA prime, which is not known to us. So we're going to keep it as VA prime, plus MB, which is 0.3, times V prime B, which is unknown to us as well. So now we're going to simplify this part over here. We're going to get negative 0.07. This is equal to 0.5 VA prime plus 0.3 VB prime. So now what we want to do is we want to write one of these, either VA prime or VB prime, in terms of the other. So we want to isolate either VA or VB. It doesn't really matter which one we choose. But for the sake of simplicity, I'm going to choose VA because all we have to do is multiply by 2 and get rid of the 0.5. So we're going to say that VA prime, or at least 0.5 VA prime, is equal to negative 0.07 minus 0.3 VB prime, which means that now we want to multiply both sides by 2 so that we can get rid of this 0.5 here. So we're going to get VA prime is equal to negative 0.14 minus 0.6 VB prime. And we're going to keep this in a box now because we're going to use it in a little bit. This is an extremely important part of the equation. So now we're going to look at the conservation of energy. So kinetic energy before the collision is equal to the kinetic energy after the collision. Now we want to expand the kinetic energy, so we're going to say that half of the mass of A times the velocity of A squared plus half of the mass of B times the velocity of B squared is equal to half of the mass of A times the velocity of A after the collision squared plus half of the mass of B times the velocity of B after the collision squared. Now we want to plug in our numbers. Just like what we did earlier over here, we plugged in our numbers and we simplified. We're going to do the same thing over here for the kinetic energy equation. So we're going to say that it is half MA is 0.5 times VA prime, which is 0.4 squared, plus half of MB, which is 0.3, times VB squared, which is 0.9 squared. Now here you might tell me, oh, but it's negative. Why did you keep it positive? Well, first of all, it doesn't really matter because even if we put it negative, the squared sign is going to make it positive. But also at the same time, there's a deeper reason for that, and that's because the kinetic energy is a scalar quantity, which means we want to keep everything as its absolute value. So we don't want to keep anything negative anyways. So we continue. This is equal to half. MA, again, is 0.5. VA prime squared, we keep it as it is, plus half MB, which is 0.3, VB prime squared. Just like what we did before, we're going to simplify this side over here. And we're going to get 0.1615. And all of this is equal to, so I'm going to calculate this. This is going to be 0.25 VA prime squared, plus this is half of 0.3, it's 0.15 VB prime squared. And just like before, I'm going to put this in a box because it is the simplest it can be. But before I actually do anything with it, what we're going to do is we're going to substitute what we have here as VA prime inside this other formula. So in a sense, or in a way, we're combining the conservation of momentum with the formula of the kinetic or the conservation of energy. So we're gonna substitute whatever we have in VA here. Instead of saying VA prime, we're going to say what it's equal to, and that is this. And the goal here, the reason we're doing this is because instead of having one equation and two unknowns, we're going to end up having no VA prime, we're going to have only VB prime. So we're going to have one equation in one unknown, which happens to be VB prime. So we're going to do exactly that right now. So we're going to say that this is all equal to 0.1615, which is equal to 0.25. Now V prime A, all of the whatever goes here is going to be squared, right? Remember, because we're replacing VA prime, so everything that's VA prime will end up being squared. So we have negative 0.14 minus 0.6 VB prime, and now plus 0.15 V prime B squared. So this is excellent because we have one equation, we have only one unknown, which is VB. These two are the same thing. So now we're going to keep going and expand this so that we can work on simplifying it. So we're going to say again 0.1615 is equal to 0.25. First, we want to expand what's inside the squared parentheses here. So we're going to notice one thing that's very important, and that is how do we expand this to begin with. So remember, this relies a lot on your knowledge of math. So you need to realize that negative a minus b all squared is equal to a plus b all squared, right? Because when something is negative in a squared, it's going to end up being, positive anyways, right, when you square it. So that's why we say that these two are equal. And when you have a plus b all squared, to solve this, you end up saying that this is equal to a squared plus 2ab plus b squared. And that is exactly what we're going to do here. We're going to change this into a plus b, and then we're going to expand it like this. So I'm going to keep this on the side for us just so that you can keep seeing it as we are solving. So what will it look like now? So 0.25, let's first change it into a plus b all squared. So this looks like minus a, so we're going to turn it into just a, so it's going to be 0.14. This looks like minus b, so we're going to say that it's plus b, which is plus 0.6 v prime b. Okay, all of this is squared, plus 0.15 v prime b squared. Next, we're going to now expand it as we see here. So again, we're going to say 0.1615 equals 0.25 and now we open a parentheses, and now we're going to expand it. So this is the a, this is your a, and this is your b. So a squared is 0.14 squared plus 2ab, so a is 0.14, b is 0.6 v prime b, this is 2ab, plus b squared, so b squared, all of this is b squared, is 0.6 v prime b all squared. And we close the parentheses so that, we remember that we want to multiply all of this later by 0.25. And then all of this is still not complete because we want to add 0.15 vb prime squared. Okay, so I'm going to get rid of this now because we no longer need it. We just used it. Now we want to expand 0.25. Remember, given that 0.25 is multiplied by everything inside the parentheses, we're going to expand it into 1, 2, all of this, and 3, all of this. Okay, so let's do exactly that. We're going to say that this is 0.1615 equals to, so 0.25 times 0.14 squared, that is equal to, well, they're giving me scientific notation, which is fine. We're going to say that this is equal to 0.0049, and then plus, and then all of this multiplied by 0.25. Now, given that v prime b is not a number, we're going to keep it as it is. So we're going to multiply 2 by 0.14 by 0.6 by 0.25. And then we're going to say whatever that is times v prime b. And putting these numbers on the calculator, you're going to get 0.042 v prime b. And then finally, this squared is basically 0.25 times 0.6 squared, and you're going to get 0.09 v prime b squared. And then finally, all of this is plus 0.15 v prime b squared. Next, we're almost there. We're almost done. We're going to bring this to the other side so that we can add these two together, or in fact, subtract them. So we're going to get 0 equals negative 0.1566 plus, here there's nothing to do, so we're going to keep it as it is, 0.042 v prime b plus this, which is 0.24 v prime b squared. So now we have this very neat and simple quadratic equation. You're going simply to plug these numbers into your calculator, and you're going to get both values of v prime b. So given this quadratic equation, we're going to get that v prime b is equal to 0.725 meters per second, or it's going to be equal to vb prime 0.9, actually negative 0.9 meters per second. Now, here it's very easy. Given that we have two options, we're going to have to reject one and accept one. And this one is going to end up being rejected. And the reason for that is, look at VB. If we go back and check what did we have as VB, the velocity before the collision, it's negative 0.9. So it's not possible that the velocity of the object after the collision is going to be equal to the velocity of the object before the collision. The collision changes the velocity of an object, so definitely the object B did not just keep going its regular route after the collision. That doesn't happen. So this is the VB that we're going to accept. So V prime B is accepted as 0.725. So this is the accepted value. So now, excellent, we have V prime B. This is awesome. We're almost there. This is almost the last step, because now what we're going to do is we're going to go back to the conservation of momentum formula, and we're going to look back at this relation, and we're going to copy it actually so that we see it all the way down. And now that this relation is clear, all we have to do is do another substitution of V prime B over here. We're going to give it the value of 0.725, and we're going to get what V prime A is. So let's plug in these numbers. So V prime A is equal to negative 0.14 minus 0.6 times V prime B, which is 0.725, and we're going to get negative 0.575 meters per second. So V prime A is equal to 0.5 or negative 0.5 0.75 meters per second. And this makes perfect sense. This one is going to the left, this one is going to the right because it's positive, this one's going to the left because it's negative. So that these numbers make absolutely total sense. And that's it. So we go back to the scenario and we now see very clearly that VB ends up moving backwards with the velocity of 0.725, and VA or VA prime ends up moving with the velocity of negative 0.575 meters per second. So that's it for this video. I completely understand that this can be overwhelming. I mean, look at this. It's an entire page worth of solutions. But this is the way to solve it. I hope the steps make sense. And that is all.